Okay. Okay. Yes. Now we are live. So welcome everyone. Welcome back to our second seminar in this session. We are happy to host Professor Sangkook Choi from QIAS to give the second seminar, and I would like to ask again Ara to introduce Professor Choi.
Thank you, and thank you very much for being with us again. So our second speaker is from QIAS, Professor Sangkook Choi. He received his bachelor degree and master degree from SNU, and he did his PhD study in the US at UC Berkeley with Professor Stephen Louis. And he moved to Locust University as a postdoc and worked there for 2 years, and moved to Brookhaven National Lab and worked there as a staff until 2020. And by day of 2020 September, he started to work as a professor at QIAS as a professor. And his research interest is quite similar with us, emergent phenomena in quantum materials, with a focus on methodology with initio calculations, including DMFT and many-body perturbation theory. And today he will talk about
the title is initio
DMFT methodologies for correlated
quantum
materials. And let's make our speaker again.
Okay, thank you very much for inviting me to present my recent researches. And my name is here. Okay, Sangkook Choi from QIAS. And my talk title is Ab initio DMFT methodologies for correlated quantum material. I know that this is really tiring schedule, so let me try to entertain you as much as I can. Okay, this is a list of the collaborators, and the main player in this talk is Byung-Kyun Kang at University of Delaware. And I also collaborating with Patrick Simon and Andrei Kutepov at Brookhaven National Lab, and Mark von Stuttgart at KCL, and Shihan Lee at University of Hamburg, and Myung-Jun Han at KAIST, and Warburg Hugo Breeder at FUMG in Brazil, and Christian Haule and Gabi Cotillier at Rutgers University. Okay, let me start my talk in a different way. We are at the verge of the second quantum revolution. In the early 20th century or late 19th century, people have found true quantum nature of electron and photon. Based on this physical understanding, people try to make use of this understanding to revolutionize our daily lives. And based on this understanding, they have realized new industry in the semiconductor and laser, and they have changed our lives. We now use the laptop and cell phones, and without this, we cannot live. And what people are trying to do nowadays is that they try to do second quantum revolution. What people are telling us is as follows. In the first quantum revolution, we have a use of the only semi-classical nature of the electrons. So people try to use true quantum nature of the electrons, and what they are telling us is that if we make use of them, then we can realize a big advancement in computing, sensing, and cryptography and network. And these are two front runners of the quantum computing devices. The first one is the superconducting qubit, and the second one is trapped ion qubit. Last year, people have realized to make 100 qubit devices, and people are trying to go further based on this development. However, there are also some challenges. That is, these two front runners are experiencing computation destroying noise sources. For the case of superconducting qubit, there are many different noise sources. The first one is the two-level system in the amorphous oxide in it. And the second example is the quasi-particle tunneling at the Josephson junction. We also have dissipation at the interfaces, and at the interfaces and surface, we have fluctuating magnetic spins, which generate one of F noises in the superconducting qubit devices. For the trapped ion qubit devices, the situation is similar. It has straight DC field, RF dissipation, surface-related E-field noise, and other noise sources. So to realize fault-tolerant quantum computing, what we have to do is we just identify all those noise sources, and we should get rid of all those noise sources from the devices. But there's also alternative way to realize fault-tolerant quantum computing. That is, let's just forget about all those front runners and think about the next generation qubit host. To search for next generation qubit host, what we have to think about is where we can find those next generation qubit hosts. Quantum material is a material class where we might be able to find next generation qubit hosts. Quantum material is a material of which properties is determined by true quantum nature of the constituent elements, and it is based on two pillars. The first one is many electron interactions, and the other one is topology. Among the quantum material of which true quantum nature is from the electron-electron interaction, we call them correlated quantum material. Correlated quantum material shows us lots of potential as a next generation qubit host. The first example is topological iron-based superconductor. Iron-based superconductor is the S-wave superconductor, and among the iron-based superconductor, there is also some really interesting material, which is iron, selenium, tellurium alloy, where we can find non-trivial band topology in its normal phases. When this non-trivial band topology, when we have this non-trivial band topology, it means that we can have Dirac-like surface band structure. When this Dirac-like surface band structure meet the S-wave superconductivity in the Berg, it means that we can have topologically non-trivial superconductivity at the surface. And if we realize this topologically non-trivial superconductor, then it means that at the boundary of this superconductor, we can realize interesting excitation, which is so-called Majorana state. Majorana state is zero energy excitation at the boundary of the topological superconductor. And people are telling us that if we make use of this Majorana state, we can realize topologically protected qubit devices. This is an indirect evidence of the presence of a Majorana state at the surface of the iron-based superconductor. And this is zero bias map at the surface, and this is the vertex. As you can see here, at the core of the vertex, we have really sharp peak, high density peak, which is telling us that we have zero energy excitation at the core of the superconducting vertex. Another example of the correlated quantum material as a next generation qubit host is quantum point defect. Quantum point defect is a defect state embedded in the large gap insulator. One of the famous examples is nitrogen vacancy center in diamond. As you can see here, we have substitution of nitrogen atom and we have vacancy right next to it. And if we just include these three carbon atom near this vacancy center, then we can just regard this one as some kind of molecular state embedded in the diamond. So interesting property of this defect state is that its ground state is degenerate, and this ground state is partially filled. So it means that we can have well-defined quantum spin associated with this defect state. And if you manipulate this quantum spin associated with this quantum point defect, we can make use of them as a unit of our information. But another interesting property is that this quantum spin is well protected by the presence of the large gap insulator, so that it is free from most of the noise sources. So I showed you two examples of the correlated quantum material, which has a potential as a next generation qubit host. So as a condensed matter theorist, what you have to do is we just try to understand the properties of the correlated quantum material from theory. Maybe the first way of doing it is we just apply the well-known working host methodology to the community, to this class of material, and see how it behaves. The well-known ab initio methodologies to the community is density functional theory and the GW. And density functional theory and GW are known as a good tool for the conventional material. Here, what I mean by conventional material is material of which property is determined by freely moving valence electron. So because its material property is determined by those freely moving valence electron, it means that the importance of the kinetic term in the electron-Schrödinger equation is more than this electron-electron interaction term. So it means that we can approximate the contribution of the electron-electron interaction term with some kind of effective term. So what the DFT and GW do is just like that. And for the density functional theory, for the effective term, they use so-called quotient potential. And for the GW theory, what they are doing is, for the effective term, they use some kind of term which is motivated by this GW diagram. And if you make use of, if you make use of those theories, the accuracy is quite surprising. For example, if we make a prediction of the ground state structure of the silicon within the density functional theory, it does tell us that its ground state structure is hexagonal diamond, which is consistent with the experiments. And for the excitation or one electron spectra, if you just calculate the spectra using GW theory, and this is the comparison between theory and experiments for the germanium, the theory is full line here and the experiment is dotted line here. As you can see here, they are matching quite well to each other. So we have well-working tools in the community and we have material interest. So next thing we can do is just let's apply those two to the material class of the correlated quantum material and see what happens. But here, what you should remember is that in contrast to the conventional material, correlated quantum material property is determined by bound valence electron, not the freely moving valence electron. And those relatively bound electrons can be found in the elements of transition metal and lanthanide and actinide, which has a 3d orbital and the 4f orbital and 5 orbital near the chemical potential. So let's just pick a validation material of lanthanum and copper oxide, and let's apply this working host methodologies to this material and see what's happening. Lanthanum copper oxide is a mother compound of qubit superconductor. And from those experiments, we know that when it is not magnetically ordered, it is insulator. However, if you do the electronic circuit calculation with the density functional theory and the GW calculation, when it is not magnetically ordered, what it tells us is that it has some kind of electronic structure at the chemical potential, which just tells us that this material is metal from those two calculations. So we know that these two working host methodologies is working well for the conventional material. Over here, we have one example where this DFT and GW fails for correlated quantum material. So we are interested in correlated quantum material, but the conclusion is that we need an ab initio theory beyond DFT and GW. So then what is our theory to make a prediction of the correlated quantum material property? So for that, we should think about what is a good reference picture to explain those electrons. So for the conventional electron, we have itinerant electron. And in the cases, we know that density functional theory or GW are really good theory tools. In these cases, the importance of the kinetic term is really important. However, in the other extreme limit, we can think about the atom arrays. In these cases, all the electrons are localized near the nucleus. And in these cases, the importance of the electron-electron interaction term becomes bigger in comparison to the conventional material cases. So in these cases, we have well-defined quantum chemistry tools such as CCSE, NCI, and so on. But however, for the electrons in the correlated quantum material, which is a relatively bound state, electrons here, they are neither fully localized or not fully itinerant. It means that we need the theory tools to understand the correlated quantum material properties. We need the emission theory tools, which is going beyond DFT and GW, and we should have some means to retain this electron-electron contribution explicitly. So we have to find such a tools. But I want to make a note that to understand the correlated electron material property is one of the great challenges in the condensed matter theory community. So we need to have a theory tools to deal with this dual nature of electron and itinerant electron nature as well as no localized electron nature. But fortunately, in the community, we already have theory tools which can deal with this dual character of electron. One of the efficient way of doing it is by using the dynamical mean field theory. Dynamical mean field theory provides a reference frame for correlated electron. So what the dynamical mean field theory do is as follows. It is just doing mapping quantum many electron problem to quantum impurity problem in an effective action. So in the left side, we have the atoms, and in the atom, we have electrons. And then in an atom, electrons are interacting with each other, and you just create all the many-body multiplets here. At the same time, electron can hop from one side to the other side. The simplest Hamiltonian we can think of to describe all this physics is a so-called Hubbard model here. We have hopping terms between different sites, I and J. And for the site I, we can have electron-electron interaction term explicitly. What the dynamical mean field theory do is instead of solving this Hubbard model, they are trying to map this Hubbard model into so-called quantum impurity effective actions, and they try to solve this more simplified problem. So in the quantum impurity effective action, we have two terms. The first term is about the electron-electron interaction for the site 0, as you can see here. And we also have electron hopping between the 0 side to the 0 side at different time. So the first term deals with band-like properties or electron hopping. And in the second term, it just deals with electron-electron interaction effect. And one thing you should see here is that all the site index is fixed to the 0. It means that this is some kind of effective local problem. And let's try. So I have introduced you to this methodology. So now we can solve it, right? So let's just solve it for the Hubbard model. So for the Hubbard model, if we solve the Hubbard model by using the dynamical mean field theory, and this is the result. So when the electron-electron interaction term is 0, it means that U equals 0. In this case, is the contribution from this electron-electron interaction term goes away. So it means that it should give us some kind of metal-like density state. So if you solve this problem using dynamical mean field theory, this is final density state. And as you can see here, we have semicircular density state with a chemical potential at the center. So we have metal here. But if we increase the Coulomb interaction to the really big value here, as you can see here, then contribution from the electron-electron interaction term dominate all the physics here. So we have a multiplex structure, or we have upper Hurd band and lower Hurd band. But the interesting thing about the dynamical mean field theory is that it can deal with those two extreme limits, and it can also deal with those intermediate region between U equals 0 and U equals really big. So it can deal with weak coupling limit as well as strong coupling limit, and it can deal with those intermediate region too. So due to this kind of theoretical power, so people try to make use of this theory for their initial calculation since then. So we have good theory, so we want to make use of this dynamical mean field theory for the initial calculation. So basic idea of the ab initio DMFT is quite simple. It is just let me use this. It is just divide and conquer. So in the material we have many electrons. Then we just divide the electron into two groups. The first one is correlated, and the other one is iterant. The main idea is that for the correlated electron, let's just deal them with the dynamical mean field theory, and for the iterant state, let's just deal with the first principle methodologies. But mathematical way of this division can be done by using projection operator in the Hilbert space. In the Hilbert space, we have some projection operator app. So from this, we can define our correlated orbitals. And then for the rest, it will be all the iterant state. But for the choice of the first principle methodologies, as I told you, we have two different ways of doing things in the community. The first one is density functional theory, and the second one is the GW. So if we combine DFT with the DMFT, this is so-called the DFT plus DMFT. And if you combine GW with the DMFT, this is just GW plus EDMFT. And between those two methodologies, there is trade-off between speed and accuracy. So if you want a really accurate result, then we can go with the GW plus EDMFT. However, we want to get the results quickly, then we can go with DFT plus DMFT. And I know that this is a theory community audience, so I want to give you more details about the ab initio DMFT. Okay, so we are now trying to solve the quantum many-body problem. So brute force way of solving the quantum many-body problem is trying to calculate the many-body wave functions. And Sung-Sub also gave us some kind of showed introduction about this kind of wave function approaches. But in the community, there is alternative approaches to solve the quantum many-body problem that is so-called functional approaches. Functional approach scheme is as follows. We just think about some kind of functional of some function Q. And usually this could be total energy, or this could be free energy, and some kind of quantity here. And we say that this quantity is some functional of some function Q. And then if we can find some, then we will try to find this kind of stationary condition. If we find the standard stationary condition of the total energy or free energy with respect to this Q quantity here, then this is a way to calculate the physical Q. And once we calculate this physical Q, then later we can use the total energy by using physical Q, and we can also make use of this Q naught for the calculation of the other quantities. One of the examples of the functional approach is density functional theory within the Hohenberg-Kohn theorem. In the Hohenberg-Kohn theorem, what we do is as follows. When you have many-body system here, we have external potential, and this external potential is defined the full many-body Hamiltonian. So in this full many-body Hamiltonian, the first way of calculating this full many-body Hamiltonian is calculating this full many-body wave functions. And once we calculate this many-body wave function, we can calculate the observables. However, the calculation of this full many-body wave function is challenging. So what the density functional theory are telling us is as follows. Instead of calculating full many-body wave function, we just try to calculate some total energy functional of density. And what Hohenberg and Kohn tells us is that this total energy functional, it has stationary condition with respect to the single particle density. So from this stationary condition, we can find the physical density. And once we calculate the physical density, then we can make use of this physical density to calculate other quantities. So instead of calculating many-body wave functions, we can make use of these functional approaches to get some information of the quantum many-body systems. And that's what exactly we do when you apply, when you make use of the ab initio DMFT methodologies. So ab initio DMFT plus DMFT can be understood in the similar way. So DFT plus DMFT can have also defined free energy functional. This is an extension of the moment functional. And this free energy functional is functional of density and Hartree exchange correlation potential. And we have local Green's function, and we have local self-energy here. And as I told you, this is functional should have some stationary condition with respect to these 4 different arguments. So the first stationary condition tells us the definition of our Hartree exchange correlation potential. And from the second stationary condition, we have the definition of our local density. And okay, like this. And from the third stationary condition, we have our definition of local self-energy. And from the last one, we have our definition of our local Green's function. And one of the ways to satisfy those stationary conditions is by making use of the self-consistent condition, but I will tell about that later. But we have some challenges here in this formalism. That is this so-called psi functional, which is dealing with the electron-electron interaction term, is not well defined. And this is this is also the same problem when you're formulating the density functional theory. So what the DFT plus DMFT do as follows: they just approximate this pi functional as a combination of the pi functional for the DFT and pi functional for the DMFT, and we just subtract the double counted contribution. And if we define our pi functional in this way, then we can have the definition of our Hartree exchange correlation functional from the pi function of the DFT. And from the second condition, we also have our definition of our embedded self-energy. But there is still some challenges. That is definition of our pi functional, which is double counted. And in the community, we have some well-defined tests for the pi functional for the double counting. And this is one of the widely used definition, which only depends on the total charge associated with the correlated orbital. And here I would like to mention that for the double counted pi functional, there is also so-called exact double counting schemes. So if you're interested in, you can take a look at it. Okay, so as I told you, from the stationary condition, we have 4 different stationary conditions to satisfy. But one of the ways to satisfy these 4 different conditions is by using the charge self-constant condition. So from the first loop, we have full Green's function, and from there we define our density, and from there we can define our full Green's function. And if we solve this loop, this is so-called density function theory loop. And from the second loop, we also have some loop related to time-to-time wind field theory. And if we solve these 2 loops self-consistently, this is the way we can get our final fully interacting single particle Green's function.
May I answer?
Sure.
So you apply the variation, the variation of which doesn't it support some local minimum?
You mean that whether it is global minimum or local minimum?
So there are, I believe, in plane space there are a lot of points satisfying the station. So then there are a lot of solutions.
Yes.
Satisfying the.
Yes.
How do you overcome this?
Okay, so in a practical situation, my answer is in twofold. First one is that usually what we do is we can, so this is about self-consistent conditions, so that if we starting our self-consistent loop from different starting point, we might get to the different, the final solution. If we just all goes into the same solution, practically we can safely assume that that is just global minima. That's one thing. And another one is that also when we, for the DMFT problem, there is also some reason where we should have this kind of 2 solution issues. But in that case, it's also depending on our starting point. If we're starting from the weak coupling limit equals 1 solution, if you're starting from the strong coupling limit equals to the other solution, but there is some known issues there. So what my final answer is that we can just change our starting point of the self-constant loop, and we just see whether we can go into the same final solution. But as you can see here, we cannot check all possible the starting point. So practically, we can check one or two in practice, and we can see where it goes to the same solution. But one of the challenges when we do the DFT plus DMFT calculation is that there is two quantity which should be determined by the choice of the correlated orbital, which is this projection operator F. So projection operator F just determine the shape of our correlated orbital, and there is two different parameters should be determined accordingly. The first one is Coulomb interaction tensor U here, which is related to the definition of our effective quantum impurity action. And the other one is double counted self-energy, which goes here. So the physical meaning of the Coulomb interaction tensor U is as follows. It is effective renormalized Coulomb interaction between this correlated orbital. So this is a bare Coulomb interaction between correlated subspace degree of freedom. However, all the other degree of freedom should be renormalized. But this value should change by the choice of the correlated orbital. One example is that just think about how we define our correlated orbital to be extended in a space. It means that in the cases, the Coulomb interaction associated with those extended orbitals should be small. So in the case, this value should be small. But we can also pick our correlated orbital should be tightly bound to the nucleus. In the cases, our Coulomb interaction tensor value should be large. So as you can see in this example, U value should be determined accordingly. And for the double counted self-energy, which is just double counted contribution from the ab initio calculation as well as DMFT, this value also depends on the choice of the correlated orbital. So that value should be chosen accordingly. However, in practice, in the practical DFT plus DMFT calculation, those two values are being chosen, and the numerical results will depend on the choice of those two values. Okay, and also I can also introduce you the GW+EDMFT approaches using these functional approaches. And for the GW+EDMFT, we can also define some free energy functional, which is so-called fine Cardinal or Luttinger word functional. This functional is functional of Green's function, self-energy, and screen Coulomb interaction and polarizability here. And we have many different terms here, but don't worry about it. It has some practical meaning. So first two terms is the free energy contribution from the single particle Green's function. And the second term is we are subtracting from the first term is that we can subtract out the contribution from the electron-electron interaction in the single particle Green's function. And for the rest are dealing with the electron-electron interaction in a really accurate way. But we have some kind of unknown here, which is so-called psi functional. And this psi functional can be chosen as any two particle irreducible diagram of the Green's function and the screen Coulomb interaction. And what the GW+EDMFT do is we define our psi functional from the GW diagram and EDMFT diagram. And if we subtract the double counted diagram, then we can define our psi functional in an unambiguous way. And we have four different arguments of our functional. So it means that we should have four different stationary conditions. So from the first one, we have our definition of exchange correlation. The first one is a GW self-energy. And second one is the DMFT self-energy. And the last one is double counted self-energy. And from the second equation, we have GW polarizability or double polarizability. And we have EDMFT polarizability, and we subtract the double counted polarizability here. And from these two different stationary conditions, we have fermionic Dyson's equation, and we have bosonic Dyson's equation here. So to realize full GW+EDMFT self-consistent loop, we have three different self-consistency here. So in the middle, we have full Dyson's equation here, but we have three different objects for the fermion and boson. One is the GW self-energy, EDMFT self-energy, and double counted self. So we have first one GW loop, which just determines our GW self-energy, and we have second double counted loop, which determines our double counted self-energy for the fermionic quantity and bosonic quantity. And we also have last EDMFT loop, which defines our EDMFT self-energy and EDMFT pluralism. But the challenge is that it is hard to implement these full GW+EDMFT methodologies in our first principle methodologies. So it means that to make use of the GW+EDMFT idea, we should have some simplifications. So my contribution in this community is I suggested some kind of partial self-consistent schemes to the community. So as I told you, full GW+EDMFT has three different loops, but here I just neglected some of the self-consistency here. The first one is the GW self-consistency. I neglected, and I also neglected self-consistency for the bosonic quantity. And for the definition of our Green's function, instead of using this fully interacting Green's function, I defined my Green's function using some kind of non-interacting Hamiltonian together with self-energy embedded with the DMFT self-energy. And I propose this kind of schemes. And let me give you some more details about it. That is, for the choice of our mean-field Hamiltonian, I picked so-called the linearized quasi-particle self-consistent GW. So what it does is as follows. So first, we are starting with some initial guess of our mean-field Hamiltonian here, and from this, we construct our quasi-particle Green's function here in this way. And from this, we can construct our GG polarizability using this quasi-particle Green's function. And then we can define our spin Coulomb interaction using this polarizability here. And we finally have our self-energy, which is fully frequency dependent. But the way how we construct our quasi-particle Hamiltonian by using this fully interacting Green's function is that first, together with this Hartree Hamiltonian, we just embed our static term of the self-energy together with a proper normalization G factor term here. And in this way, we just construct our Hermitian quasi-particle Hamiltonian. And if we solve this self consistently, and this is so-called LQSGW scheme. And for the case of the bosonic bifield, I just use a CIP scheme, which is a way to calculate the effective Coulomb interaction within GW theory. And for the double counting self-energy, what we learned from the full GW+EDMFT is that our double counting self-energy is so-called local GW. So to summarize my scheme of the LQSGW+DMFT, this is a simplification of a full GW+EDMFT. And one of the advantages of this methodology is that this is a parameter-free method. That is, for the case of the DFT plus DMFT, there is no systematic way to calculate the Coulomb interaction tensor and the double counting self-energy. However, in these cases, we have a way to calculate it. And since its first invention, we have to the validation of this methodology on different classes of correlated quantum material of charged transfer insulator, iron-based superconductor, and narrow-gap correlated insulator, and so on. So let me show you some of the examples. That is iron antimony 2. Iron antimony 2 is narrow-gap correlated semiconductor, and it has its importance for the thermoelectric properties. So first, since after we invented our schemes, then we asked experimentalists to measure its alpha spectra of this material. And this is alpha spectra from the XYS line in this material. As you can see here in this energy range, we have three bands. One is alpha band, and second one is beta band, and the third one is gamma band. So the way alpha and beta are meeting with each other is at a point. However, if you do the calculation of this material within the LDA, as you can see here, we only have two bands, and the way alpha and beta are meeting with each other is 2 point, not the 1 point here. If we do the GW calculation, the situation is similar. We only have 2 bands, and these 2 bands are meeting at 2 points. However, if we do our LQSGW+DMFT calculation, we have 3 bands here, and the way alpha and beta are touching with each other is at 1 point. So it shows us the best agreement with the experiment.
other in simple LDA plus DMFT.
So LDA plus DMFT has some weaknesses here. So this material is known as Narrowgate correlated semiconductor, which means that we have gap here. But if you apply LDA plus DMFT, it cannot open a gap. And the second material classes of validation is charge transplants layer. We have lanthanum copper oxide and nickel oxide, and we have spectral function of lanthanum copper oxide and nickel oxide here. And we have 3 different calculation and experiments. First one is LDA plus DMFT, second one is LQSGW plus DMFT, and the last one is experiments. And for the lanthanum copper oxide, we have experimental data here. We have 2 peak structure. The first one is from the oxygen P and copper D, and second peak is from the lanthanum F. But if you do the LD plus DMFT calculation, as you can see here, lanthanum F peak is too shallow, and the oxygen P and copper D peak is also too shallow. However, those 2 shallowness has been fixed by using LQSGW plus DMFT. And for the case of nickel oxide, the conclusion is similar. We have 2 peak here from the experiments. However, if you do the nickel oxide LD plus DMFT calculation, this peak are too shallow. However, this shallowness has been fixed if you use LQSGW plus DMFT.
So the nickel oxide GW is better in the sense of the describing PD hybridization material.
So the way how we understand it of this nickel oxide results is as follows. So this peak has the hybridized peak from the oxygen P and nickel D, and for the oxygen P, this kind of bands electronic structure can be built better with the GW, not the DFT.
Therapy position of the P.
Yes. So from this kind of methodology development and the validation project, we finally released open source ab initio packages for the correlated quantum material. The package name is DMFT. And in these packages, we have, there are many different, advantages. So one of the advantages is as follows. So as I told you, for the description of correlated quantum material, what we do is usually divide and conquer. For the alternate state, we have DFT and GW. And for the correlated state, we can have DMFT and some kind of simplified way of doing DMFT, which is so-called Kurzweiler here. So we can think of 4 different combinations here. But in these packages, we have 3 out of 4 these methodologies here. We have various flavors here. We also have LQSGW plus DMFT schemes in it. And impedance solver part has been GPU accelerated. And for the GW and LDA part, we are using open source packages so-called flat MBPT. And this is US DOE funded open source package. Okay, so we did the validation and we release our packages. So it's time to find the interesting physics in real material. So target system we picked is infinite layer nickelate. Infinite layer nickelate is nowadays really hot material. That is, we have found the superconductivity in 2019, if I remember correct. So material, one of the examples is neodymium, strontium, nickel oxide here. And if we dope the system at a particular doping, we can find really beautiful superconducting dome. And one of the interesting things about this material is as follows. This material is isostructural to cuprate. One of the cuprate mother compound, which is calcium copper oxide, has the same structure with lanthanum nickel oxide. And from the ab initio calculation, although this is really on the debates, But general belief is, if I believe is that phonon is not a main mechanism to induce this superconductivity here. So those two things have similarity to the qubits. However, there is also some differences. That is, in this mother compound, it is weakly insulating, not fully insulating. Weakly insulating can be understood as bad metal. And in comparison to the qubits, it has two bands at the chemical potential in contrast to the one band for the case of qubit. And in its mother compound state, at low temperature, there is no magnetic order in comparison to the qubit cases. So there are some similarities and differences between the qubit and nickelates. And there are many different questions related to nickelates. But one of the questions that I had is, where is the correlated metallic base is from? So there are two different routes to realize correlated metallic bases in the multi-band system. So this is the interaction term in the simplest. I just wrote down the interaction term in the simplest way. This is so-called Kanamori form. In these cases, the interaction term can be written in this way. First, we have term related to total charge. And second, we have term related to total spin. And third, we have term related to total angular momentum here. And there we have a coefficient which is defined by the property U and point J here.
You consider the full d orbital or
No, this is, if I remember correctly, this is formed for the three orbital cases, but it can be also generalized to the full 5 d orbitals, but this so-called Kanamori form.
you the Kanamori form in the 5D.
Okay. So this is for just explanation of the physics, but this is not the interaction term I use in the numerical calculation. I just wanted to use this term, this form of this interaction term for the explanation. So we have two coefficients here. One is the Howard U and second one is Jones J. And Howard U term try to minimize the total occupation for the correlated orbital. And the Jones J try to maximize the total spin and total angular momentum here. But as you can see here in this Hamiltonian, we have two different coefficients. So there is two different way of realizing correlated metallic bases. First case is that when the U is the origin to realize correlated metallic base, and the second case is so when the J is the origin of the correlated metallic bases. In the first case, we call them Punto-metal, and the second case is we call them this is multi-metal, and the second case is we call them Punto-metal. But for the simplicity, I will not describe all the physics here, but I will just tell you how the phenomenology for different cases are different. So for the cases multi-metal, because this is related to the large U value, it means that we have large separation between the upper Hubble band and lower Hubble band. So it means that at high temperature, if we measure its tensile state, it should show us to this two-hump structure. And for the case of the local susceptibility in the orbital and spin channel, because the contribution from the J is really minor in these cases, so it means that we have Curie-like susceptibility for the spin and orbital channel. But for the case of Punto-metal, the situation is different because in these cases, J is an important player. So it means that separation between upper and lower Hubble band are small. So it means that if we measure its tensile state, it should show us this single hump. And for the case of the local susceptibility, because there is a spin orbital separation as described by the Sangkook here. So orbital channel should be fully screened, so it should be Pauli-like, but the spin channel should be not screened, so it should be Curie-like. But important message here is that we have two different classes of the Punto-metal and multi-metal. So we have a well-defined way to differentiate those two classes. So it means that to answer this question, what you have to do is if we can measure those two quantity, or if we can calculate those quantity and make and then we can tell us and we can say whether it is Punto-metal or multi-metal. But however, in reality, in the community, this is not an easy question. The first, there is no direct experimental proof yet about this question. And second, to answer this question, there are many different people have tried to use DFT+DMFT methodologies to answer this question. However, different group goes into the different conclusion. Although they use the same methodology of DFT+DMFT, some group says that it is quantum metal. However, some group says that this is a molten metal. The reason why they are going into different conclusions, although they use the same methodologies, that DFT+DMFT is parameter dependent method. So they have used different U value and double counting scheme. So they go into the different conclusion. So there is no experimental direct proof yet. And this parameter dependent method gives us different results. So one way of solve this problem is that we might apply parameter-free emission methodologies for correlated quantum material and see what it says. But as I told you, I have my methodology, which is LQSGW+DMFT, which is parameter-free. So I might be able to answer this question.
very confusing.
Okay.
Molten metal.
Concept of molten metal. For the physics, maybe we can have a discussion after this talk.
Original mode is one band model. But the multi-band model both not easy to say.
In what sense?
Hubbard model is not simply determined of one band. Hubbard model itself is that there are a lot of orbital.
Yeah.
So Olen mentioned orbital selectivity. Orbital selectivity is also in the multiplet sense, the local multiplet has a lot of multiplet structure.
Yeah.
Not single multiplet is not simply determined of the charge gap. Even in local site, there are a lot of multiplet, Tn multiplet or Tn minus Tn plus one multiplet is very complex.
So I don't know if I understand your question, but okay, let me try to explain the physics of the molten metal. Molten metal can be understood as some kind of metallic state really close to the mode phase boundary. So it is right next to the mode phase boundary, it is still metallic. However, this kind of local correlation determines the bad metallic behavior.
But the superconducting is actually charging interaction.
Yes.
Is determined by the U minus 3J.
Yes.
Not U.
Yes.
So that easy to in the even in the boundary, we can increase the J value, but it's the same for J supercoupling almost zero near the phase boundary, and we could supercoupling is very large boundary and the both region is the same.
So okay, let me tell you the criteria to define quantum metal. So in the community, there are two different ways to define the quantum metal. One is the spin-orbital separation, as Sangkook introduced, and the other one is so-called Janus effect.
But the Janus is I did computer.
Okay.
Very sorry to interrupt, but we have just 5 minutes.
Okay.
Perhaps we can discuss later.
Okay. So I will give you an introduction about the Janus effect, but if you go with it, then I'll be able to answer your question. So I have a new methodology here. So let's see what my methodology tells us. My methodology tells us that nickelate is quantum metal. So if you calculate the spin and orbital susceptibility, as you can see here in the spin channel is Curie-like. However, in the orbital channel is Pauli-like. And if you calculate the extensive state at high temperature, it shows a single hump behavior. And there is some ED calculation which reproduces the Briggs data on this material. And from the ED calculation, we have some information of our many-body configuration in the d orbital. And from there, they have some number here. And we can also do the same calculation with my methodology here. And they are matching well to each other. So this is just research, and I'm just interpreting my data, and I'm just saying that LQSGW+DMFT are telling us that nickelate is a quantum error. I'm not saying that this is the method, so this should be the real physics. However, I'm just interpreting that my methodology tells us that this is quantum error. But if this conclusion is what's really happening, then this is really big claim. That is, I'm proposing a new paradigm of unconventional superconductivity in this way. So for the qubit, reference picture is the charge distance per insulator. However, for the iron-based superconductor, the reference picture is 5 orbital quantum error. But if this claim is true, this is what's really happening, then this what I'm telling you is that I'm telling you that either nickel-based superconductor is the 2 orbital quantum error, and this is the first example of the 2 orbital quantum error and its superconductivity.
Is it possible to vary the temperature in calculation?
Yes. So as you can see, this is the temperature dependence.
So what is the
So this is the spin channel susceptibility, which is steady as a function of temperature in the spin channel and the orbital channel.
what is the lowest temperature?
Lowest temperature in this case is, if I remember correctly, it is 100 Kelvin. May I continue?
So I have a question.
Yes.
So you mentioned the R configuration there.
Yes. Ours.
R in the orbital configuration.
Yes.
Did you include the orbital in the infinite solver or?
So in our calculation, we have 10 spin orbital from the nickel 3D atom, nickel 3D subshells as our impurity. And I don't know if I answered your
And
question.
R is rare earth contribution, right?
Yeah, this is just notation for their ED calculation. But we can have we just interpret this one as our, if I remember correctly, this one as our, this is triplet. And if I remember correctly, we interpreted this one as a singlet contribution.
In the D bin point.
In the ED calculation, it is included. However, in our cases, it is contributed, it is included as a back.
At the best.
Yes.
I contributed nickel has already orbital page almost A1 almost 0, right?
Say that again, please.
Different from the T2G system, easy average of easy orbital state is 0. Value is 0.
What value?
Easy orbital has you measure the orbital angular momentum of easy system. It's already 0.
Oh, this is the almost so its occupation is between 8 and 9, and it's close to 9, but it's not fully 9.
Yeah, but fully 9 is this is
You mean to crystal field?
even in this orbital Y orbital is fully occupied.
No, it is not fully
I
occupied.
don't know. Even in the orbital in local sighted, easy orbital is only this orbital angular momentum is 0.
No, it is close to 3. For the EG, it is close to 3. Occupation is not 2, but 3.
Still, EG has no orbital angular momentum. So
It is. Can you continue the discussion after this talk? Okay, I have something to deliver. So as I told you, to full GW+EDMFT implementation is challenging, but good news is that for the last 2 years, we have tried to implement this full GW+EDMFT in a first principle fashion. But before doing that, we need to have some kind of evidence that once we realize these new methodologies from first principles, and we was curious whether we can find a new physics. So as a test bed of these methodologies, we picked a modern Hamiltonian, and we try to solve some of the physics using modern Hamiltonian using GW+EDMFT methodologies, and we try to see whether we can see some differences when you use these fancy methodologies. So the system we have focused on is the superconductor, and we have 2 different superconductors. One is qubit, and the other one is iron-based superconductor. For the case of this qubit phase diagram, we have the antiferromagnetic ordered phases here, and we have a superconducting phases there, and we also see some charge order phases. But for the IW superconductor, we have a superconductor here, and we have a spin density wave. However, we was not able to see some good signature of the charge order, the phases in these cases. So our initial guess was that charge order might be able to be found in this IW based superconductivity here, and there might be some intrinsic entanglement or some interplay between the Hooke's physics and the charge order phases. So to see such kind of physics here, we picked our degenerate three-band model here. So this is a degenerate three orbital system Hamiltonian here. We have a non-interacting sim here, and we have a local Hamiltonian defined using the Kanamori form. And in addition to this, we have a non-local electron-electron interaction term here. So this local term will deal with the quantum physics here, and this non-local Hamiltonian will deal with the charge order physics here. But for the local physics, we know that DMFT is a really good tool for that. And we also know that for this non-local Coulomb interaction, GW should play some essential role here. So that's the reason why we pick this Hamiltonian, and we see the physics related physics of this Hamiltonian using this GW+EDMFT methodologies. Okay, so this is a final result. And for this Hamiltonian, we have three different interaction coefficient in the interaction term. One is the U term, and the other one is V term. We also have the Hund coupling J here. And this is phase boundary between these two different phases. The first phase is so-called homogeneous phase, where we have at different sides, we have two electrons. But in these cases here, we have so-called charge ordered phases or valence skipping charge ordered phases, which means that we have three electron occupation and one electron occupation alternated here. And this is phase boundary, which is obtained from the atomic limit calculation, which means we just neglected the Hoping effect. And if we do the real numerical calculation of the full GW+EDMFT for this modern Hamiltonian, this is the final result. And as you can see here, the difference between the atomic limit calculation and this numerical calculation is not that much. However, we see some differences here in this region. What you can see is that the region of the valence skipping charge order has been increased. So it means that there is some enhancement of the charge order instability in this region. And the way we see the charge order phase is that we calculate this charge susceptibility, and we some divergences in this pi in some case spaces. So we just take a look at what's happening in this region, and we just see some of the physical quantity. One is the so-called dynamic contribution of the spin susceptibility, and the other one is the low frequency behavior of self energy. And if you take a look, if you measure these quantities, it just has its relation to the quantum matter physics. But the conclusion here is that in this region, quantum matter physics is really essential and strong. So it means that the final conclusion is that when there is strong quantum metallic phases, there could be large enhancement of the charge order instability. But the interesting thing here is that this kind of charge order instability enhancement can be only found when you do the GW+EDMFT calculation. If we calculate this phase boundary within just DMFT calculation, we don't see this kind of enhancement. If you're only using the GW, there is no enhancement too. But however, to see this physics, we need to combine those two methodologies, and we are able to see those physics. So from this model calculation, we have convinced that implementation of full GW+EDMFT from first principle methodologies might show us some kind of new physics in the real material. So we are working on it, and we finished it. We finally implemented fully self-consistent GW+EDMFT from first principles for the first time. And this paper will be submitted soon to the community. So there is some validation there. So one example is strontium vanadium oxide. For the case of strontium vanadium oxide, although this is also topic of debate, but general belief about this material is that this material is weakly correlated. And this is DFT band structure, and this is LQSGW band structure. As you can see here, with the chemical potential, we have several bands, although there is some defective normalization. Overall, we have some band which is causing the chemical potential here. If we make use of an LQSGW+DMFT calculation, this is our final result. However, if we make use of our full GW+EDMFT calculation, we obtain the similar band structure, which is signature telling us that this material is truly weakly correlated material. And if we do the electronic structure calculation for the nickel oxide, which is charged transfer insulator, and the DFT and LQSGW telling us that there is electronic structure here when it is not magnetically ordered. And this is the conclusion which is inconsistent with the experiments. However, if we do the calculation using LQSGW+DMFT or full GW+EDMFT, which do not require any adjustable parameters, as you can see here, we can open a really beautiful gap. So to conclude, ab initio DMFT is a promising methodology to understand the properties of correlated quantum materials. And when DMFT is combined with many body perturbation theory, such as GW, it can be free from adjustable parameters. And we have a package so-called COM suite. And this is ab initio packages to support ab initio DMFT methodologies. And this is constantly evolving. Thank you for your attention.
I have some questions, so I hope the time allows. So first question is a difference between the DMFT and EDMFT.
Yes.
So in EDMFT, you include the boson to degrees of freedom.
Yes.
And what is the physical entity corresponding to this boson degrees of freedom?
So difference between the EDMFT and DMFT is as follows. The first one is the starting Hamiltonian is different. In the DMFT formalism, for the interaction part, what it includes is only the local interaction term, and it goes in DMFT. And for the EDMFT, starting point is not the Hubbard model, but it is extended Hubbard model where we have non-local interaction term. But as you know, the basic idea is of the DMFT is that we would like to solve some local effective interaction. So it means that as we did for the hoping terms, to remove this non-local quantum interaction, we should have some kind of effective term related to boson quantity. That's the differences between the EDMFT and DMFT.
Yes. Then that interaction, what is the range, typical range of that non-local interaction?
So for the formalism, there is no constraint or some restriction about the range of the non-local interaction. We can include as much as we can.
And the second question is you showed this say controversy between the US group and the Austrian group regarding this nature of the nickelate. And then from your point of view, what does the Viennese scores got wrong?
No, I didn't say it is wrong. But
how they are different?
So
specifically.
More specifically, my viewpoint is as follows. So ab initio DMFT is a projection-dependent method. What I mean by projection-dependent method is that once we pick our correlated orbital, then there is all other parameters should be determined accordingly. I think different groups have picked different orbitals by choosing different size of the energy window. That's first differences. And second difference is that for the correlated orbital, there is a Coulomb interaction tensor, and there is Coulomb interaction parameterization of U of J, U and J, but I think they use different value. The Gabi and his colleagues picked the smaller value, for example, for the U equal 5, and the other group who is supporting the molten metal scenario, they picked the value of 8 or 10. Simply just parameter is different.
So what would be the best way to really say verify?
So verify is the simplest way of doing it is if there is experiment.
Which experiment?
Any experiment which can tell us the spectroscopy information. And if the numerical calculation can reproduce such information, that will be the best. The simplest one is the RPET spectrum. Then we can just make a comparison between the theory and experiment directly by using single particle Green's function. However, in this material, there's no RPET data. There is several weeks data. However, the weeks calculation is, there is also some more complexity. So it makes the story or this kind of situation worse. That's my answer.
Sorry, I have just one last question. So also recently, the DFT plus U plus V method was proposed as alternative to GW. Then what is your point of view in the context of this system?
Okay. So we have, in the community, we have two advanced methodologies. One is the GW, and the other one is DFT plus DMFT. And the local approximation to the GW could be understood as the DFT plus U. And the static approximation of the DFT plus DMFT can be understood as the DFT plus U. So this is different way of the extending the physics on top of it. But recently, Youngwoo and his colleagues have extended this DFT plus U method to include the V, the terms in it. But my view about it is that it's really good news for the community. That is, as according to their claim, what they are telling us is that they can calculate the electronic structure with the GW accuracy in a more efficient way. But then that means is that we can make use of their schemes for the material discovery. I think that is the way to go for them. I think Young, of course, is the same idea, and I really like it.
Then can it be used as the say in combination with DMFT?
I think the he is working on it.
Okay.
Yes. So maybe key point is about double counting compensation between Newton and correlated of the dynamic correlation. This key quantity.
Yeah, thanks.
Okay, any other question?
Is it possible to estimate force load by relation scheme?
You mean using full GW plus EMFT? Yeah, but as I told you, this whole scheme is from the free energy function, which is by Cardano. It means that if you have free energy, we can calculate forces and total free energy and everything. However, we are not there in principle. In practical, we haven't tried it yet. But within the DFT plus CMFT, there is also already force formalism as well as implementation, and people are using it.
So what is the computation cost of the quantum impurity solver, the CTChem solver in cases with screened Coulomb interaction?
You mean the how for the EDMFT?
Yes.
Yeah, it is the same. The same as DMFT. With bosonic bias field is going to its bosonic bias. So for the EDMFT formalism, we have frequency dependent U. So we just separate the frequency dependent U into static and the dynamical term. The effect of dynamical term can be integrated out, and it changes the value of the effective hybridization function. So in that way, the numerical cost is the same.
So when you say the cost the same, you're using comparing for example, Rutgers CTChem C and that one in using CPU base.
So it doesn't matter whether it's CPU or GPU. The effect of this dynamical screening just go into the change, to change the hybridization function effectively.
So I'm asking in a practical sense.
Yeah, in a practical sense.
Because there are no other GPU accelerated CTChem sequence by.
If I remember, as far as I know, there is no accelerated. Yeah, but it doesn't matter with the GPU or CPU. Just in principle, it is the same. So it means the implementation sense, it is the same.
Another question.
In the previous slide, the example of Mr. on the arm side, you presented the possibility of GW+DMFT and full GW+EDMFT. But when I look at the AK omega, it looks different. So without the experimental data, which scheme is more reliable?
So for the nickel oxide, maybe for the nickel oxide, For the nickel oxide, the data, if I remember correctly, the only data is not the angle resolved one, but the angle integrated one. But if I remember correct, although this looks quite different, but when you make a comparison to the experiments, if I remember, I could be wrong, but GW+EDMFT shows us better, better agreement with the experiments. Yeah, for the strontium vanadium oxide, we have another validation material of strontium vanadium oxide. The interesting conclusion is that actually among these four, if you make a comparison to the experiments, LQSGW is the best one.
I think we can continue the discussion at dinner time, so let's think.